Hey everyone, it's Jesse with a quick video about games and networking. Now today I wanted to talk a little bit about what I consider to be the holy grail of game networking, and that is peer-to-peer connections. Now peer-to-peer connections really have a lot of advantages. By their very definition, they are the most efficient route between two hosts. If you have a host in one city and another host in another city, they can communicate peer-to-peer. It's not routing to a third city that's out of the way, right? The routing is going to be the most efficient possible in a peer-to-peer connection. Now, the other advantage, of course, is there is typically no expensive infrastructure to maintain. Non-peer-to-peer connections, like going through a server, a dedicated server somewhere, or perhaps using a networking service like Steam or Epic Games, those connections will have to go through a third-party server, which is expensive, and also it may not be geolocated in a location that is convenient for your players. That's where you have games that have, for instance, North America servers, Europe servers, etc. If you have to connect to a server that is not local to your place of residence, it is going to add a lot of latency. So if you imagine a game with a North American server and two European players, well, all of that traffic is going over an undersea cable and back on its way to the other host, to the other client. So peer-to-peer is great. Why doesn't every game use it? Well, of course, there's value to companies like Steam and Epic in selling their network. But in addition to that, peer-to-peer is actually pretty challenging. So we're going to talk through why it's challenging, as well as some of the ways that we can overcome it, potentially enable peer-to-peer for games like Cause Monarchy. By the way, I'll be referencing Cause Monarchy a lot in this video. If you haven't checked it out, go to fraudsclub.com. It is an epic RTS in the Brood War engine. So let's start by thinking about how web traffic works. Now I'm going to gloss over a lot of networking here just to give you the high points of how this works. But if you have a computer trying to reach a web server, as you can see on my screen share here, that computer can send requests and receive responses to the web server just fine, as long as they have an IP address that is reachable from the computer. But actually networks are far more complex than this. You're likely part of a local area network. Now, local area network is like this bubble around your computer. It is a security and a multi-user connectivity feature that enables multiple users on the network to connect. What I mean by that is when a connection goes from this computer in our local area network to the web server on the right, that connection is sent through another device, typically a router, or in the industry we might call this a gateway and use this kind of icon for it. Now, the gateway is responsible for ferrying connections between the greater internet and our local area network. And in order to do so, it has to keep track of multiple users in the local area network. For instance, if we have 3 computers in that local area network, it has to ferry traffic from all of those computers to and from the internet. Now, the way it does this is using a technology called Network Address Translation, or NAT. NAT is a technology that allows it to have an internal scope of IP addresses that are assigned to these devices inside the bubble. And then, of course, it has a different IP address that's assigned by the ISP that it's going to use for external communication to the web server and back. And so it's going to have addresses assigned to computers 1, 2, and 3 here. And when those computers send a message to the server, it's going to keep track of which computer sent the message so that the return traffic can get back to the same computer. How does it do this? Well, it uses something called a port. Now, ports are an additional number that's attached to the connection that's used to identify individual hosts as well as individual applications on the network. So, for example, if we have a web traffic, your web browser is going to send traffic to port 80. Port 80 is used for HTTP, or perhaps port 443 for HTTPS. But in any case, that traffic's going to go from that host to the web server's IP address with a destination port of 80. Now, the router is going to translate that port into something random. You can see it's changed that port 80 into port 5454. Now, it's still sent to the web server over port 80, but the return port, the return address on that parcel, on that packet, is 5454. That's different than what we initially requested over here. And that allows the router to keep track of that connection, right? If a different computer on this network also requested that same website, same port 80, it would have a different return port on that message. And so the traffic would get back to the right place. So after this request is sent to the web server says, great, here's my data. I'm going to send it back to port 5454. The router, of course, then forwards that to computer number 1 because it remembers that connection. Now, why does this make peer-to-peer difficult? Well, the difficult thing about peer-to-peer is you're in a bubble, but so is the person that you want to talk to, right? If we want to establish a game between these two users on two different local area networks, they both are behind those network address translation routers where they have different external IP addresses and random port assignments on external connections. So for instance, if we have Cause Monarchy on port 6111, it's going to send that traffic to port 6111. The router is going to change that to something random. It's going to say from 45341 to 6111. The router on the other side doesn't know that there's any traffic coming from port 45341 to port 6111. It's not anticipating any traffic. The technical term is it doesn't have that in its NAT table. It keeps track of open ports and ports that traffic are being sent from. So it's going to say, I don't know what to do with this traffic, and it's never going to make its way to our client on the right. It's going to drop that traffic and it's not going to be replied. It's not going to get to where it needs to go. However, there is one thing about this that we can think about in making this type of connection work, which is as soon as this is sent, the router on the left is now expecting a reply on 45341. You could say that port is open on the left-hand side, and any traffic that goes to that port for a brief period after this attempt has been made will be sent back to this specific host on this specific port. Right, so it's going to translate it back, even if it doesn't come from this specific host. It doesn't really keep track of that. So port 45341 is now available. And that means we can use it for UDP hole punching with an ICE session using a stun server. Now, if you've ever seen that trope in science fiction where you have a energy shield that goes down briefly as soon as a weapon is fired, and if you're really clever and you're really fast, you can fire back through that hole before it closes up. That's essentially what we're doing here. A hole is punched through that firewall, through that NAT, when there's that outbound connection attempt, and you can sneak an inbound connection back through that hole if you are clever and if you're quick. So let's talk about how this works. We need basically two things. We need a stun server and a signaling server. Now, they could be the same server, but for the sake of explaining this, we're going to think about them as two separate servers. So the way that we make this happen is we have client number 1 here on the left send a message to the stun server using the stun protocol. And what that does is it establishes an outbound session to that stun server, which is publicly addressable. It's not behind a NAT. It's not in a bubble like our peer-to-peer session is going to be. And the stun server observes the connection details from that connection attempt. It says, hey, this connection came from port 45341. So it then sends back a message to the client in our local area network and tells it what its external port is. So now this client knows that when it sends messages, then those messages are going out port 45341. There's a hole in the firewall here that redirects back to it, basically. So it can then talk to the communication server, which again is also a publicly available server, and it can send what are called ICE candidates. Now, ICE candidates are potential port options that might work for this connection. There are multiple network interfaces on each of these devices, including a local one and over the internet one. Maybe there's a VPN interface like Radman or similar, and there will be potential port options for each of those interfaces. So those are all opened and sent back. And by the way, the stun server keeps sending messages back and forth in order to keep that port open. We're keeping that external hole in the firewall open using that stun server and protocol. So client number 1 sends the signaling server hey, I'd like to talk to client number 2, and here are my external connection details. The signaling server then relays that information to client number 2 here, which by the way had previously established a session as well with the signaling server, so they have a connectivity path there. And then client number 2 will say, great, I've got an incoming connection, I better do my stun ICE process as well. So they log the port of the other device. Their port is 54341. They'll go ahead and do a stun session with the stun server, figure out what their external port is. They will go ahead and send that back over the signaling server. And then the client on the left will then know what the port is for the client on the right. So they both know each other's external port at this point in time, as well as each IP address that's also sent as part of the ICE candidates. So once they know that information, they can go ahead and try and establish a connection. Now I mentioned there's multiple candidates, multiple interfaces they could try to connect on. They will actually try and connect on all of those, and they'll find the best one. So maybe there's a public path, maybe there's a path through a VPN server like Radmin. It will try all of those different interfaces. As soon as they get a connection, it will go into a connected status. And as soon as they've figured out which connection is the best, they will land on that, and then peer-to-peer connectivity is established between them. So a little bit of a process to make this happen. Again, this is called ICE, and there are libraries that make this happen. For instance, I'm using the Juice library for C++ to establish a peer-to-peer connection between clients. There's also an additional add-on you can do called Turn. What Turn does is it typically is an add-on to this stun server that then routes connections through it if peer-to-peer couldn't be established for some reason. Now, without using a Turn server, we can use a public stun server. For instance, Google has a public stun server anyone can use, and so we can use that for free. If we want to add Turn, we're routing packets through that server, so there's a cost for that. And we get back to all of those issues with non-peer-to-peer networks. But it is a fallback option for if you have a situation where you can't get through the NAT on both of these networks in order to establish peer-to-peer. So hopefully that quick overview was helpful and interesting, gives you an idea of what we're working on as far as building a peer-to-peer networking for Cause Monarchy. Hoping to have some proof of concept working soon. In any case, hopefully that was interesting, and I hope you have a good day.